All right, welcome to the 4.2 lecture over the unit circle. Let me just Okay, so the objectives for this particular section are, first we're going to use a unit circle to look at what the trigonometric functions actually are for real numbers. We'll talk about domain and range of sine and cosine. Exact values for certain trigonometric functions, pi over 4 being a pretty important one that you'll use a lot, so we'll definitely drill down into some of those. We'll talk about even and odd functions when it comes to trigonometric functions, and also a quick little refresher on what even and odd functions are. We studied those in college algebra, so hopefully there aren't too many cobwebs that need to be cleared out from that, but if so, I'll certainly be able to help you understand that a little bit better as well. And then periodic properties, and actually that says we're going to do stuff with the calculator, but because this lesson was already extremely long, I'm leaving off the calculator part, but it is in your textbook. And it's no different than doing it by hand. It just does it for you in your calculator. But you can go, that's the very end of 4.2, so if you want to read up on that and make sure you can use your calculator, you can read that part of the section, or you could just go into YouTube and find a video, and I'll try to go find one and post in this section on using the TI-83 or 84 for trigonometric functions. So we'll go ahead and move forward with the lesson. Okay, so the first thing that we run across in this particular lesson is the idea of a unit circle. And a unit circle is a circle with a radius of 1. So it just makes all your calculations nice and neat. You've got set points that you know. So this point right here is the point -1, 0. This is the point 0, 1, and this is the point 0, -1, obviously. You have the equation for a circle there, which was also addressed in college algebra. If you need a refresher on just the circle itself, that is section 1.9. of your textbook, and in my math lab you've got access to all that old stuff too if you want it, and if you want practice problems on that you can go into the study plan under section 1.9. But we have the equation for the circle there, x squared plus y squared equals the radius squared. So let's go ahead and move forward. Okay, so in our last lesson in 4.1, we gained the knowledge that the angle theta, the central angle theta, the measurement of that can be given by the measurement of the arc length divided by the radius of the circle. And now we're going to apply this specifically to the unit circle. So how does this change basically? And this H should not be there. It should just be the real number T. So because we're working in the unit circle, we're going to call the central angle, we're going to name it T instead of just that general theta that we used in 4.1. So since we're dealing with the unit circle, our radius is 1. So if I start working with this, I have theta, well, in the unit circle, we call that T equals S divided by, I can plug in 1 for the radius, and anything divided by 1 is just itself, so I end up with T equals S. What does that mean in regards to my circle here? What that means is that the angle T is equal to my arc length when I'm dealing with the unit circle. So if you look here at this first illustration, on the left, you can see they have that arc labeled as T and they have the angle labeled as T there, and in the second picture as well. This is how that happened. It's not because it's some new amazing formula that you get when you're dealing with the unit circle. It's solely based on the fact that the radius of the unit circle is 1. So it changes. Well, it doesn't change it, but it allows that angle measurement to be equal to the arc measurement. Are y'all good with that? Okay, Roy says yes. Marcus, if you're with us, just give me a green check to let me know you're ready for me to move forward. Okay, Marcus types yes, so I'll clear that out and move forward. Okay, so now we're going to move into the 6 trigonometric functions. We're just going to kind of name them here, and then in the subsequent pages we'll look at how do you find these, what actually are they. But trigonometric functions involve real number inputs represented by T. In the figures, that should say to the left. It says above, not because that's what it says on my, well, actually it does say above on my notes, and I kind of pulled this, I pulled this directly from my note sheets and put it onto a PowerPoint. So to the left there. And the outputs involve the point P, so notice P is on the circle over here, P, and that point P has the coordinates X, Y, just like normal. So when we're looking for the trigonometric functions of T, we're looking for the trigonometry or the trigonometric functions of that angle. And in the unit circle case of the arch as well, and what we get out from it are these points here. So on the unit circle, we can have sine. You'll never see it written this way. You'll see it abbreviated. That is not sin, that's sine. And then we have cosine, tangent, cosecant, secant, and cotangent. And I have to say this, I think your book does a really poor job of showing you what this actually is. And so I pulled in some drawings that I found online to help us better understand what these are and what they look like. So it'll be really important with this section for you to follow with your notes and make sure you're referring to your notes, because like I said, I just don't think your book does a great job of describing this to you. Okay, so this this slide is jam-packed. But before we look at the top yellow part here, let's just look at this middle drawing that has SOHCAHTOA written over it. And I'll tell you what the SOHCAHTOA is. I'm sure you've probably heard that in the past. But I found this illustration and thought it was fantastic because it visually tells you or shows you what these things actually are that you're finding. So your 6 trig functions can be thought of as a length related to the unit circle. So in following this line of thought, my line, and let me get my colors ready here. Okay, so my line, AF, it touches the circle, and it's the line formed by dropping a line straight down to the x-axis that's going to form a right angle there. So that is the sign, and it is always opposite your angle theta. All right, and then we have the cosine, and the cosine is the length from it runs along the initial side of the angle, so I'm going along the x-axis, and it's that length from the vertex of the angle along the initial side up to that line where the sine has dropped down and hit the x-axis. So that little blue line is representative of the cosine. And then the other one that is contained with the triangle is the cosecant. And I'll tell you why it's named that. So here's the cosecant, and the cosecant basically goes, it moves along the terminal side of the angle to go and touch the cotangent. All right, so let me describe to you what that actually is. A secant line is a line that intersects a curve in 2 places. So you can see the secant line, let me get a darker color green there, that one's a little too light. You can see the secant line that they have drawn, okay, it's coming down, it crosses the curve there, and if I continued with that secant line, it would intersect the circle in 2 places. So that's why it's called a secant line, because it intersects the circle in 2 areas. Co, the prefix co means with. So once again, that cosecant is part of the secant line, but it's just the segment that goes all the way up to the cotangent line and stops. So that's why it's called cosecant, because it's along with the secant line, but it stops, whereas the secant line continues. Now, the tangent line, a tangent line in general is a line that intersects a curve in one place. So I have the tangent line that touches the circle at or on my initial side at 1, 0, and goes straight up, and it ends where it intersects the secant line. So the cotangent line is the segment that starts at 0, 1 and ends where it intersects the secant line, the cosecant line, and the sine. Let me draw my sine in again. So this is what we're figuring when we're actually doing these calculations with these trig functions. And SOHCAHTOA right here is just a mnemonic device that helps you to remember how to calculate the sine, the cosine, and the tangent. So if we move to this third illustration here, this triangle is representative of the right triangle that was formed in this illustration on the inside of the unit circle. So you can see I have a radius of 1. Here's where it intersects my circle. And then I've got that arc length that is equivalent to the measurement of my angle there. So what we find is that if we want to figure the sine of theta, then all we have to do is from theta, that interior angle there, we divide the opposite side over the hypotenuse. So let me name the sides of the triangle here for you. Let me get a different color. So obviously the hypotenuse is always going to be the hypotenuse. The hypotenuse is always the angle that is directly across, I'm sorry, the side of the triangle that's directly across from the right angle. And then we have opposite and adjacent. The opposite is always going to be directly across or opposite of angle theta. And then we have the adjacent side, so it's actually touching angle theta. So this is the adjacent, and this is the opposite for angle theta there. So the SOHCAHTOA comes into play by saying sine is opposite over hypotenuse, cosine is the adjacent divided by the hypotenuse, and the tangent is the opposite over the adjacent. So once again, all three of these illustrations are not in your textbook, but they are in the note sheets that I gave you. And if we look here at this first illustration, it just actually gives the coordinates for that point on the circle x, y. So the sine is y over 1, which is the opposite over the hypotenuse, which we just get y there. The cosine is the adjacent, so the x value over the hypotenuse, which is 1, so we end up just getting x. Tangent is y over x, so opposite over adjacent. And then we also have cosecant, secant, and cotangent. Cosecant is the inverse of sine. So cosecant is 1 over y, or the hypotenuse over the opposite. Cosecant is the inverse of cosine. I'm sorry, secant is the inverse of cosine, so that's 1 over x, and then cotangent is the inverse of tangent, x over y. So basically all you need to do is, you know, put to memory the actual numerators and denominators that will give you each of these. SOHCAHTOA can get you started with it, or if you prefer to think of it as X and Y, your sine is always your Y value, your cosine is always your X value, tangent is always Y over X, and then you have their corresponding inverses. So I've marked this slide all up. Are y'all good so far and following? Okay, good deal. I'll move forward. Okay, so, ooh, did I skip a slide? Hang on. I know I put that slide in there. Oh, I put it after. Let me see if it'll let me move the slide. It will. All right. So, let me click. Okay, sorry, I'm back with y'all. I think that I got my note sheets out of order. It's not the slides that are out of order, it's my note sheet. So let me get these slides back in order because I started moving them around. And let me make sure that, okay, let me go back one. Okay, so is this the next thing that y'all are seeing in your notes? Please let me know if you printed out your notes and are following along. Yes, good, great, excellent. Okay, so maybe I have them in order like they should be now. All right, let me just get my slide changer back off to the side here. All right, so we're ready to look at this. So I'll just go ahead and write this on the slide so we have it to look at. We have the sine of t equal to y. The cosine of t is equal to x. The tangent of t is equal to y over x, and then we have their inverses. The cosecant of t is equal to 1 over y. The secant of t is 1 over x, and the cotangent of t is equal to x over y. So we're just going to perform these calculations using our trigonometric functions there. All right, first off, sine of t. Well, I'm given a point here, and I have coordinates for each of my, or I have the coordinates of my point there. So we know that the sine of t is just equal to the y value, so that's just 1/2. Because remember, it was opposite over hypotenuse, and our hypotenuse is 1. So that's 1/2 divided by 1. So it just ends up being, or it looks like it ends up being the coordinate itself, but it's not the coordinate itself, it's that length. The cosine of t is x, square root of 3 over 2. Easy enough. The tangent, this is where it gets a little more complex. So the tangent is equal to the sine, which is 1/2, divided by the cosine, square root of 3 over 2. And now if your skills with rationalizing denominators and stuff like that aren't so hot, you'll definitely want to go back into the prerequisite material and make sure that you've got that radical stuff down, because we're about to have to use it here, as well as working with fractions. You've got to be able to work with fractions to be able to make it through trig. So this is equal to, I never divide fractions, I multiply by the reciprocal, so 1/2 times the reciprocal 2 over the square root of 3. And here, my 2's divide out, and I'm left with 1 over the square root of 3. However, we have to rationalize that denominator, and I do so by multiplying by the clever form of 1, square root of 3 over square root of 3. 1 times the square root of 3 is just the square root of 3. And basically in the denominator here, I'm squaring a square root. So the square root of 3 times the square root of 3 is the square root of 9. Square root of 9 is just 3. So square root of 3 over 3 is my tangent. Let me stop there and make sure everybody followed that math magic right there. Good. Okay. All right. Well, then I'll continue. That's great that y'all all understood that math there, because that's going to keep me from having to do a lot of explaining, because this mathematics right here is going to come up again and again and again. So make sure you have that down pat. All right, cosecant. Okay, so that's 1 over y. That's 1 over 1/2. Once again, I never divide fractions. I multiply by the reciprocal. So 1 over 1 times the reciprocal of 1/2 is 2 over 1, which is 2 over 1, or just 2. And the secant is 1 over x. So 1 over the square root of 3 over 2. Here we go again. 1 over 1 times 2 over root 3. So that's 2 over the square root of 3. I've got to rationalize that denominator. I can't leave a root in the denominator like that. So square root of 3 over square root of 3 gives me 2 square root 3 over 3. And finally, the cotangent is x over y. So that's square root 3 over 2 divided by 1/2. Never divide fractions. Square root of 3 over 2 times the reciprocal 2 over 1. My 2's divide out, and I'm left with square root of 3 over 1, which is just the square root of 3. So I'm going to go back and I'm going to circle all of my final answers here. So the sine of t was 1/2. The cosine of t was square root 3 over 2. The tangent, square root 3 over 3. Cosecant, 2. Secant, 2 square root 3 over 3. And cotangent, square root of 3. Y'all good with all of those trig functions on that one? Roy, Marcus, and Madison all say yes. All right, I'll move forward. Okay, so same thing here, but we have a different angle that we're working with. We are working with the angle pi over 2. And we found out in 4.1 that that corresponds to a 90-degree angle. And so we have the point P here, which is 0, 1. And these calculations are going to be much quicker and easier than that last one we looked at. So here we go. Sine of pi over 2 is equal to my y-coordinate, 1. Oh, that's just the sine, sorry. The cosine of pi over 2 is equal to my x value, which is 0. The tangent of pi over 2 is equal to y over x. Well, division by 0 is undefined. The cosecant of pi over 2 is 1 over y. Well, y is 1, so that's just 1 over 1, or 1. Hopefully y'all are beating me to the punch here and already have all these done. Secant of pi over 2, and feel free to answer if you'd like in the chat window and try to beat me. I have, for secant, I have 1 over x. That's 1 over 0, which is also undefined because division by 0 is undefined. And then cotangent of pi over 2 is equal to x over y, so that's 0 divided by 1, which is just 0. So I'll go back and mark my final answers on each of these. I have the sine of pi over 2 is 1. The cosine of pi over 2 is 0. The tangent of pi over 2 is undefined. And if you think about the tangent, I'd have that line out here, and it's not going, if I go to my point, P and drop that line down, look where it drops. It drops down the y-axis. And so I don't have an intersection with the with that sign that I was looking for. So it's undefined. And computationally speaking, it's undefined because you can't divide by 0. But we can see what's going on there visually speaking or graphically speaking. So the cosecant is 1, the secant is also undefined, and the cotangent is 0. And if nobody raises their hand, I'll go ahead and move forward. Okay, so just another problem to look at. Now we're going to look at the angle pi. So this is a special angle. It's a straight angle, so we're going to have some more funkiness, just like we did pi over 2 there. So let's go for it. These are going to be short and sweet as well. So the sine of pi is just the y value, and you can see our point there is 0. Cosine of pi is 1. The tangent of pi is 0. I'm sorry, it's -1. My bad. Roy, I'm surprised you didn't jump all over that and say, Miss Gore, it's -1. I'm just messing with you. 0 divided by -1 is 0. The cosecant of pi is 1 over y. So that's 1 over 0, which makes it undefined. The secant of pi is 1 over x, so that's 1 over -1, which is just -1. And the cotangent of pi is x over y, so -1 over 0, which is also undefined. Okay, so we've just practiced finding the trig functions for first just a random angle, and well, actually it's not so random once we drill down deeper into all of this. And then we found them for pi over 2, which is that 90-degree angle, and then we found it for pi here, which is the 180-degree angle. Okay, so believe it or not, we're halfway through our slides. And I know y'all are looking at the time going, oh my God, she's only halfway through, but we'll push forward. All right, so trigonometric functions at t equals pi over 4. So we've already discussed that pi over 4 is one of those special angles that we'll be working with a lot. So I figured it would be good measure to do our trigonometric functions for that one as well. We have the point P on the circle, point AB there. So, and we have the angle pi over 4. We'll go ahead and move forward and look at how to actually, I hope I gave myself another slide to do this, and I didn't. Awesome. So I'm going to have to, let me draw a white box over all this, and so I have room to work. I should have given myself a clean slide. I'll draw another one. Like magic. Okay. So the first thing that we need to figure out are the actual coordinates for point P there. And if you look back in our lesson from 4.1, we figured out that the coordinates of P for an angle pi over 4 are square root of 2 over 2, square root of 2 over 2. So those are the coordinates for that point P there that form the angle pi over 4. All right, so now we're ready to go ahead and burn through the trig functions with it. So the sine of pi over 4 is the y-coordinate. Well, once again, it's not the actual coordinate, it's that length from the x-axis or the terminal side of the angle up to the circle. So the cosine of pi over 4 is the x, square root of 2 over 2. The tangent gets a little more interesting, of pi over 4. So that's y over x, square root of 2 over 2, divided by the square root of 2 over 2. So we've got to go back to our fractional math here. I'm going to multiply by the reciprocal, 2 over square root 2. This is pretty nice because look what happens when I divide out common factors. 2 divided by 2, square root of 2 divided by the square root of 2. So I'm left with just good old 1 there. the cosecant of pi over 4 is given by the inverse sign, so 1 over square root of 2 over 2. That's 1 over 1 times the reciprocal 2 over square root 2. So we're going to have to rationalize the denominator here. Going to multiply by the clever form of 1 square root 2 over square root 2. And I end up with 2 square root 2. Okay, the square root of 2 times the square root of 2 is the square root of 4, so that's just 2. And then my 2's, my factors of 2 divide out there. So I'm just left with the square root of 2 for the cosecant. The secant of pi over 4, I'm not going to do, because when you inverse the cosine there, you get 1 over the square root of 2 over 2. So it's just the square root of 2. You can see the work there above. And finally, we have the cotangent of pi over 4. That is square root of 2 over 2 divided by square root of 2 over 2. Anything divided by itself is just 1. There you go. Y'all ready to move forward? Okay, good deal. Okay, another loaded slide here. Now we're moving on to the idea of domain and range of these, of the sine and the cosine function. And out of the 6 trig functions, the sine and the cosine are the ones that are going to keep on coming back, that you're really going to probably be sick of working with by the time we're done here. And I've got the wrong slide up again. Okay, I'm just going to say this and y'all are going to ignore it. Damn it. Give me 2 seconds. Because I know that, let me just ask you this before I start flipping slides. Is this the next thing on your page? I don't think it is because it's halfway down the page. We should be talking about even and odd functions. Okay, Madison's typing. Thank you, Madison. It's before the problem we just did on my paper. Oh, okay. So I put it in the wrong place. I should have put it before the last slide. So we'll go ahead and talk about even and odd then. Or I'm sorry, domain and range. Sorry about that. All right, so you'll have to go back if you're following along in your notes. I really do apologize. I don't know how I got so out of order with my notes. Actually, I do know they're not sitting in a notebook like they should be, and I grabbed them and they fell out of my hands. And they don't have numbers on them, which is another dumb thing. So let me find. Okay, so that should have been before this page. All right, I think I'm good now. Okay, so talking about domain and range of the sine and the cosine functions. So once again, I just reminded you the sine of t. Now my pen's not working. Ugh. Thank God it's almost the weekend. My pen is completely frozen. Can y'all hear me still? Yeah, I can see that it's registering me. Here we go. Okay, y'all see where I was just trying to write all over the place there? Okay. All right, so sine of t is y, cosine of t is x. So because t, I'm right here in the center, because t can be any real number, the domain of the sine function is, okay, so it can be any real number, which means it's negative infinity to positive infinity for the domain. If you recall from 4.1, we kept moving around and around and around the circle, so we have indefinite amount of domain that we can put in there, the set of all real numbers. The radius of the unit circle is 1, and the dashed horizontal lines in the figure, so right here and here, show that y, so your vertical position, cannot be less than -1 or greater than 1. In other words, it's never going to go past any of these boundaries. And I know that that seems a little like ridiculous to state that since you're looking at it in the form of the unit circle. But once we move to seeing how this function plays out through the domain in the xy plane, it'll be apparent why we need to define the domain and range here. Thus, the range of the sine function is -1 to 1. And those are brackets because it is inclusive. There is a value at y of -1 and y of 1. And since I have an output value there, I have to use brackets to include those in the range. All right. Just the opposite for the cosine. So I'm just dotting these lines a little darker for you. Still dealing with the unit circle. So because t can be any real number, the domain of the cosine function is also -infinity to positive infinity. The radius is 1, and the dashed vertical lines show that x. This one's showing x. That x cannot be, it can't be less than -1 or greater than 1. So we're restricted there. Okay. All right, and this was showing us how to find those coordinates of the pi/4 function that we got, that we've already been through. And remember, I just wrote, oh yeah, the coordinates for that point there are √2/2, √2/2. Here's how we got that. We have the equation for the circle, x² + y² is 1. In this one, we have AB, so A² + B² is 1. Well, A equals B in this case, so A² + A² is 1. I'm just substituting A² for B² there, so 2A² is 1. Divide both sides by 2. A² is 1/2. A is the square root of 1/2. You don't have to take the positive and the negative into consideration because we've already looked at the fact that it's not going to be negative. We're not going to have a negative length there. So A is equal to the square root of 1/2. A is equal to the square root of 1 over the square root of 2. A is equal to 1 over the square root of 2. I rationalize. And this is where we got the coordinates of those points are square root 2 over 2. So this is A and B there for pi over 4. I truly apologize. Okay, I truly apologize. Oh, I did give us room to work it. I truly apologize that I got these so far out of order for y'all. So we've already worked this. We ended up with the sine of pi over 4 is square root 2 over 2. The cosine of pi over 4 was square root 2 over 2. The tangent is 1. The cosecant. Please do not base your evaluations of this class on this lesson here. We ended up getting the square root of 2. The secant, or at least don't base it on the organization of this lesson. Square root of 2 and the cotangent is 1. All right. Okay, now we're to the point of where I thought we were supposed to be in our notes a while ago. Even and odd. It's okay, we all have those days. Yeah, I've tended to have quite a few of those days here lately, and maybe my luck will get a little bit better. All right, so we saw during college algebra that a function is even if f of negative x is equal to f of x. In other words, if I take a function and I plug in negative x wherever I see x in that function, I'm going to get out my original function. So no signs change if a function is even. The exact opposite is true if a function is odd. If a function's odd and I plug negative x in, I get out the opposite of f of x. In other words, every single one of my signs change. So I just wanted to remind you of what the phenomenon of even and odd functions are in general. So using this figure to the left here, we can show that the cosine function is an even function and the sine is an odd function. So we have this point, cosine of t, sine of t. So this point here is represented because we know we get the cosine of t with the x value and the sine of t with the y value. So that's the point cosine t, sine t. This point Q down here has got the same exact x value. So that's still cosine t, but it's got the negative y value. So that's the cosine of okay. Let me stop here. I want to be consistent with what I have written off to the other side. It is the same y value, and that's what shows that it's even because it doesn't change, but we're taking the cosine of negative t there. So this is the cosine of negative t, and this is the sine of negative t for the coordinates there. So the x coordinates of both p and q are the same, meaning that the cosine of negative t is equal to the cosine of t. This denotes that this is an even function. In other words, when I plugged in negative t, I got out my regular function. And by contrast, the sine of negative t is equal to the negative sine of t. So let's give these numbers just to solidify our understanding here. Say this was the point, oh, I don't know, 2, 3. Then this would be 2, -3 down there. So hopefully that helps you understand what it's saying. So since we get the opposite out there, this says, okay, this is an odd function. And this information at the bottom just states this for you. And then it also shows that there are other functions that are even. Well, there's one other trigonometric function that's even, and then there are 3 other trigonometric functions that are odd. Okay, so using even and odd functions to find values of trigonometric functions. So we have the secant of -pi/4. And if you look back at the last page, you see that the secant is an even function. So what we should expect is that the secant of -pi/4 is the same exact thing as the secant of pi/4. And we've already done the work for the secant of pi/4, and we found that the secant of pi/4 was the square root of 2. By contrast, the sine of -pi/4, well, the sine function is an odd function. So this is the same thing as the negative sine of pi/4. Well, the sine of pi/4 was square root 2/2, and we need to take the negative of that. So we found that by using our even and oddness of the functions there. That's it for those 2. Are y'all good to move forward? Okay. Okay, so the fundamental identities here. Many relationships among the 6, there are many relationships among the 6 trigonometric functions. These relationships are described by using what we call fundamental identities. These identities are equations that are true for all real numbers for which the trigonometric expressions in the equations are defined. So we have reciprocal identities, and the sine function is the reciprocal of the cosecant. So I'm looking right there. Cosine and secant. So that's why we had them lined up that way last time. Tangent and cotangent, and then just the opposite for the cosecant. We have 1/sine, secant 1/cosine, cotangent 1/tangent. And then we also have quotient identities, and these are pretty important to memorize. I would definitely suggest putting these to memory. And the reason that these are so nice, you can get these 2 at the bottom from playing with the ones at the top, but it would behoove you just to memorize these instead of actually doing that calculation. I mean, we can see that tangent is 1/cotangent, but it's nice to know that cotangent or 1 over the cotangent is equal to the sine over the cosine, instead of having to do all of that calculation between. So tangent of t is equal to sine over cosine. Cotangent is cosine over sine. So we'll use those properties in these next problems. Okay, so we're given that the sine of t is equal to 2/3, and the cosine of t is equal to the square root of 5 over 3. And they're asking us to find the values of the 4 remaining trigonometric functions. So we have the tangent of t is equal to, we can use the quotient identity that says it is the sine of t over the cosine of t. And that is equal to 2/3 divided by square root of 5 over 3. 2/3 times 3 over the square root of 5. That's a square root. That's an awful root. There we go. My 3's divide out. 2 over square root 5, multiply by root 5 over root 5, and I get 2 square root 5 over 5 for the tangent. The cosecant, so we have that the cosecant is 1 over the sine of t. So that's 1 over 2/3, 1 over 1 times reciprocal, 3 over 2, and I end up with 3/2. Stop me if I'm going too fast through these. Secant of t is equal to 1 over the cosine of t. So that's 1 over square root of 5 over 3. 1 over 1 times the reciprocal, 3 over square root 5 is just 3 square root 5. I need to rationalize. So I get 3 square root 5 over 5. And finally, the cotangent of t from my quotient identity is given by cosine of t over sine of t. Cosine is square root of 5 over 3, and that's divided by 2/3. So I have square root 5 over 3 times 3/2. My 3's divide out, and that's square root of 5 over 2. So let me just indicate my answers here. Okay, my tangent is 2 square root 5 over 5. My cosecant is 3/2. My secant is 3 square root 5 over 5, and my cotangent is square root of 5 over 2. Y'all good to go? Yes, yes, yes. Very good. Okay, so we have good old Pythagorean identities. These will be very useful for you this semester. This is another piece of the notes that you will want to set to memory because we will be using them a lot. And what we find out, these all follow from the Pythagorean theorem, a squared plus b squared is equal to c squared. So I'm not going to take the time to derive all these formulas for you. That would add about half an hour to this video, and I just don't want to do that to you. But if you want to see how they're derived, I'm happy to meet with you, or I'm sure you can find a video on YouTube of how the Pythagorean identities are derived. But like I said, these would be good things to put to memory. They're very useful when you're working with trigonometric equations. So, and by the way, this picture is not in your book. The yellow strip down there is what your book gives you. But I definitely thought it was a good idea to see, you know, visually speaking, what you're actually figuring out here. So I'll move forward. Okay, so we have a problem that we're given to work here, and it says to use the Pythagorean identity to solve. And the Pythagorean identity that we're going to need to use, since we're given the sine, and we're asked about the cosine, we need to use that particular Pythagorean identity that says sine squared of t plus cosine squared of t equals 1. And note, they would like us to find this for values between 0 and pi over 2. So we'll start with our identity. Sine squared t. Whenever you use a formula, it's always a good idea to write it down. That way you don't have to spend as much time trying to memorize it. You'll just know it if you write it down every time you use it. And I already know what the sine of t is. The sine of t is 1/2, so I can trade that out and say 1/2 squared plus cosine squared t equals 1. 1/2 squared is 1/4 plus cosine squared t is 1. And I'm going to subtract 1/4 from both sides. Those make a 0 pair. And I'm left with the cosine squared of t. Well, 1 minus 1/4 is 3/4. And I don't want to know what the cosine squared is. I want to know what the cosine is. So let me actually come back here and take square root of both sides there. And I end up with cosine of t is equal to the square root of 3 over the square root of 4, which is the same thing as the square root of 3 over 2. Thank goodness we did not have to rationalize that denominator this time. That's it. Y'all good? Excellent. And Madison says, yes, we are nearing the end, I promise. Okay, so now we move into the idea of a function being periodic. And what that means is that, well, your book's definition of a periodic function to me is quite confusing. But when you look at the picture down below, it's not that bad. But basically all it says is that that if you have a point in space and you're adding 2 pi to it for either sine or cosine, remember 2 pi is a full revolution through the circle. It says you're going to end up back at the point you started out with. So right here, you see sine of t plus 2 pi is the same thing as the sine of t, because you end up back where you started. Same thing with the cosine. Cosine of t plus 2 pi brings you back to the cosine of t. So we say that the period for sine and cosine is 2 pi. Now the period for tangent and cotangent is pi. You end up in the same position that you started out with by adding pi to, or subtracting pi from your t value. So because these are cycles that it moves through, that's why they are called periodic. Okay, so we can use the properties of periodic functions to have an easier way of finding out the values of the trig functions. So I'm going to be kind of clever with these. We have the cotangent of 5 pi over 4. Well, that's the same exact thing as the cotangent of 1 pi, and I really don't need to write the 1, but I'm doing it just for, teaching purposes. 1 pi over 4 plus 4 pi over 4. So all I've done is split that 5 up into 1 and 4. Now notice my 4 pi over 4, those 4's divide out. So what I'm really doing there is I'm adding pi to 4 pi, to pi over 4. I'm taking a cotangent, so that's a full period that I've added onto it, so that's the same exact thing as the cotangent of pi over 4. I don't really need that extra period in there. And we figured out earlier that the cotangent of pi over 4 is just 1. And if you're oh, where'd she get that 1 from? Just go back and look at our figurings for pi over 4. All right, so if we look at the cosine of negative 9 pi over 4, well, the cosine is an odd function, so I can say that's the same thing as the cosine of 9 pi over 4, which is the same thing as the cosine of 1 pi over 4 plus 4 pi over 4 plus 4 pi over 4. So 4, 4, and 1 give me the 9 pi in the numerator there. Well, those 4's divide out again. So what I've actually added on there, I have the cosine of pi over 4 plus pi, which is the cosine of pi over 4 plus 2 pi. There's your period right there. So I really don't need that because I know I end up at the same place. So this is the same exact thing as the cosine of pi over 4. And once again, we found earlier that that's the square root of 2 over 2. Are y'all good with using those periodic properties? Madison, you still with us? Okay, she's away. All right, I'll go ahead and move forward. Okay, so I included this explanation of the periods here. So you can see in each of these there's this factor of n, meaning you can multiply by as many of those factors, or you can multiply by any factor you want to, and all you're doing is circling around that many times. So you can see they just end up adding up or coming out to be the original functions, sine of t, cosine of t, and tangent of t, if you're just going around in circles. Now, I did want to show you all this real quick because this really gave a fantastic picture of what a periodic function is, and I actually have it pulled up on my web browser. So I'm going to take y'all, I'm going to share my desktop and pull that up because I really want y'all to see this, and this is the last thing and we'll be done. Okay, so y'all can see another error message from Blackboard. I was really fighting with it earlier. Let me open up my web browser here. And so this is just a wiki page. And hopefully y'all can see that movement okay. So you can see how the cosine and the sine function, as they move forward through the domain in the positive direction, are actually formulated. And I just thought this was the coolest little animation because it really brought the idea of a periodic function home. You can see that they're both bound in their vertical direction by positive and negative 1. They're never going to fall outside of that until you start translating them. And you can see, because this thing keeps on going, that domain is negative infinity to positive infinity. So that was all I wanted to show y'all with that. I just thought that was a cool little animation and really helped to help wrap the brain around it. Let me come back to our whiteboard. And that's all I have for y'all today. Do y'all have any questions about anything before we get out of here? None that Roy can think of. All right. Well, Marcus said, okay, y'all are saying no, you don't have any questions. I'm like, oh no, a red X. All right, good deal. Thank you three so much for joining me this afternoon. I appreciate y'all's dedication to being present in the lectures. It really does help me out, especially when y'all catch the mistakes I make. That helps out a lot. So y'all have a wonderful afternoon. Have a great weekend, and hopefully I'll see y'all next week. Thank you, Roy. You too, Madison. Thank you.